So now that we've solved systems by Gaussian elimination or Gauss-Jordan elimination, the question is, what are the tools that I can use to simplify the matrices, to reduce them? And it turns out there's only three things, and they're called elementary row operations. So you're going to use these three operations, and only these three operations, to reduce your matrices. And the first one is you can add a multiple of one row to another. So this is where we would say something like replace row 2 with row 2 minus 3 row 1. So that would be taking a multiple of row 1, say negative 3 times row 1, and adding it to row 2. So addition subtraction is kind of built into the same operation because you can use negative multiples. You can switch two rows. So I could just say take row 3 and row 2 and switch them around. Right? Just switch the order that they're in the matrix. And you can multiply a row by a non-zero constant. So we did things like this where we'd say replace row 2 with 1/5 times row 2. And that was division, right? But we just made it a multiplication operation. So all these three things are okay to do because the rows are representing equations in a system. And we can add multiples of one equation to another, right? We talked about that in the first video. You can switch the order that the equations come in, so you can switch the rows because it doesn't matter what order the equations are written in, the solutions are the same. And you can multiply any constant times both sides of an equation. That means we can multiply a row by a constant. So we say that two matrices are row equivalent if one matrix is the result of a sequence of row operations on the other matrix. So if I have a matrix and I do a row operation, and I get another matrix, these matrices are not equal anymore. Something has changed. Two matrices are not equal unless they have the exact same entries in the exact same places. But we're going to call them row equivalent if you can do a row operation to get from one to the other, or any sequence of row operations to get from one to the other. So when you're working the problems out, you don't want to write equals. We get in the habit of just writing equals for the next step of our problem, but these matrices are not equal. They're not the same. So we have a symbol for row equivalence, and it's the tilde symbol. So you just can write a tilde if you do a row operation from one to the other, if you want to write something in between, And if I want to do another one, then I'll say this matrix is row equivalent to this matrix because I did a row operation. Okay. And if two augmented matrix systems are row equivalent, then they have the same solutions, which is kind of necessary, right? Because we're trying to find the solution to the original system. So I want to find the solution of this guy here. So everything I do, I need the solutions to be maintained throughout the problem. So these row operations don't change the solutions to the system because they're just things you can do to equations normally to solve equations anyway. So we want row equivalent matrices if we do the right operations. And if we do them correctly, as long as you do these three row operations and you do them correctly, you're not going to mess up the solutions to the system. Now, you might not get closer to the answer. You can get in these kind of loops if you're not doing these in a logical order. You can kind of create more work for yourself. So you want to be efficient when you're doing the row operations, and you want to make sure you're following the steps and taking advantage of things that come up. You don't have to do them in in an exact perfect order all the time, but you want to be smart about how you do the row operations, or you could get yourself in a mess. Now, you can't mess up the solutions. You could still get your way back, but it'll take a little bit of practice to solve these systems efficiently, and that's what you want to do.